Imagine a world so distant, so cold, it feels like the edge of forever. A place where the sun is just a bright star in an endless night, where mountains of ice rise from plains of frozen nitrogen, and where a single day lasts longer than a week on Earth. This is Pluto, the dwarf planet that's captured our imaginations for nearly a century. Once hailed as the ninth planet in our solar system, Pluto was demoted in 2006, sparking debates that still echo in classrooms and observatories. But its story is far from over. Today, Pluto is back in the spotlight, not for some catastrophic collision, but for what it teaches us about the delicate dance of celestial bodies, the forces that shape our cosmic neighborhood, and the tantalizing possibilities of worlds beyond our own. Join us as we unravel the mysteries of Pluto's orbit, its strange connection to Neptune, and why this tiny, icy world continues to challenge everything we thought we knew about the solar system. Let's start with a question. What makes Pluto so special? Discovered in 1930 by Clyde Tombaugh, a young astronomer peering through grainy telescope images, Pluto was a puzzle from the beginning. It wasn't like the other planets. While Mercury, Venus, and Mars trace neat, nearly circular paths around the Sun, Pluto follows a wildly elliptical orbit, like a cosmic roller coaster. It takes 248 years to complete one loop, meaning that since its discovery, Pluto hasn't even finished a single lap around the Sun. Picture that for a moment. A journey so long that no human alive today will see Pluto return to where it was when Tombaugh first spotted it. But the real intrigue lies in how Pluto moves, a path so peculiar it seems to defy the rules of the solar system. Pluto's orbit is not just stretched. It's tilted, slanted at a steep 17 degrees compared to the flat plane where most planets travel, known as the ecliptic. Imagine the solar system as a spinning record, with the planets gliding along its grooves. Pluto, though, is like a rogue note, cutting across the record at an angle, dipping below and soaring above the paths of its neighbors. And here's where things get even stranger. For about 20 years out of its 248-year orbit, Pluto swings closer to the Sun than Neptune, the eighth planet. Yes, the tiny dwarf planet, barely 2,400 kilometers wide, sneaks inside the orbit of a gas giant 17 times its size. This orbital quirk raised eyebrows early on. How could a small body like Pluto cross paths with a behemoth like Neptune and not end up in chaos? The answer lies in a cosmic choreography, a gravitational dance perfected over billions of years. Pluto and Neptune are locked in what astronomers call a 3:2 orbital resonance. For every 3 orbits Neptune makes around the Sun, Pluto completes 2. This isn't a coincidence. It's a delicate balance, like 2 dancers moving in sync to avoid stepping on each other's toes. Their orbits are synchronized so precisely that even though Pluto's path crosses Neptune's in projection, they never come close to colliding. At their nearest approach, they're still separated by millions of kilometers, with Pluto's inclined orbit keeping it safely above or below Neptune's plane. This resonance is a testament to the intricate mechanics of our solar system, where even the most chaotic-looking paths find stability through the invisible hand of gravity. But why does this matter? Pluto's orbit isn't just a curiosity. It's a window into the forces that shaped our solar system. To understand this, let's step back to the early days of our cosmic neighborhood, some 4.6 billion years ago. The solar system was a turbulent place, a swirling disk of gas and dust where planets were born. Giant planets like Jupiter and Neptune didn't form where they are today. They migrated, their massive gravity reshaping the orbits of smaller bodies like Pluto. Some astronomers believe Neptune's outward journey pushed Pluto into its eccentric orbit, trapping it in the 3:2 resonance we see now. This gravitational tug-of-war left Pluto in the Kuiper Belt, a vast ring of icy bodies beyond Neptune, where it reigns as one of the largest known objects. Studying Pluto's orbit helps us piece together this ancient history, revealing how the planets settled into their current places. Now, you might be wondering, if Pluto's orbit is so stable, why do we keep hearing dramatic stories about cosmic collisions? Let's set the record straight. Despite what some sensational headlines might suggest, there's no evidence that Pluto and Neptune are on a collision course. The idea likely stems from a misunderstanding of their orbital crossing. Early astronomers, when they first realized Pluto's path intersected Neptune's, worried about potential chaos. But decades of observations and computer simulations have shown that their resonance keeps them safely apart. The gravitational influence of Neptune, along with Jupiter and Saturn, acts like a cosmic guardrail, nudging Pluto's orbit to maintain its stability over billions of years. Even tiny deviations, which could grow chaotic in other systems, are kept in check by this intricate balance. To bring Pluto's story to life, let's talk about the mission that changed everything: New Horizons. Launched by NASA in 2006, this spacecraft traveled for nearly a decade, covering 5 billion kilometers to reach Pluto in July 2015. When it arrived, it sent back images that left scientists speechless. Pluto wasn't just a blurry dot anymore. It was a world of towering ice mountains, smooth nitrogen plains, and a heart-shaped region dubbed Tombaugh Regio, named after Pluto's discoverer. The mission revealed a surprisingly active world, with signs of geological processes reshaping its surface, despite being so far from the sun's warmth. New Horizons also studied Pluto's moons, especially Charon, a moon so large it's almost half Pluto's size, making them a binary system locked in their own gravitational dance. The data from New Horizons didn't just show us pretty pictures, it deepened our understanding of the Kuiper Belt, where Pluto resides. This region, stretching beyond Neptune, is a cosmic attic filled with remnants from the solar system's formation. Think of it as a time capsule, preserving icy bodies that never coalesced into planets. Pluto, with its complex surface and atmosphere, is a key to unlocking the secrets of these distant objects. By studying its composition, mostly rock and ice, with traces of methane and nitrogen, scientists can infer what other Kuiper Belt objects might be like. This knowledge is crucial for future missions, as we dream of exploring even farther reaches of the solar system. But Pluto's story isn't just about science. It's about how we define our place in the universe. In 2006, the International Astronomical Union reclassified Pluto as a dwarf planet, a decision that sparked heated debates. To be a planet, a body must orbit the sun, be spherical, and clear its orbit of other objects. Pluto checks the first two boxes but fails the third, as it shares the Kuiper Belt with countless other bodies. This reclassification wasn't a demotion in importance, but a recognition of the diversity of our solar system. Pluto became the poster child for dwarf planets, a new category that includes objects like Eris and Ceres. The debate forced us to rethink what a planet is, reminding us that science evolves as we learn more about the cosmos. Let's zoom out for a moment and consider the bigger picture. Pluto's orbit, with its wild swings and steep tilt, challenges our assumptions about how planets behave. It's a reminder that the solar system is not a static place, but a dynamic, ever-changing system governed by gravity's invisible threads. The same forces that keep Pluto and Neptune from colliding also shape the orbits of comets, asteroids, and even the planets we call home. Understanding these forces helps us predict the future of our solar system. Will it remain stable for another billion years? Could a rogue asteroid disrupt this delicate balance? These are questions astronomers tackle using powerful simulations, modeling the paths of celestial bodies over eons. The study of Pluto also has practical implications. The New Horizons mission showed us what's possible when we push the boundaries of exploration. It took years of planning, engineering, and collaboration to send a spacecraft to a world so distant it takes light over 5 hours to reach us. The lessons learned: how to navigate vast distances, communicate across billions of kilometers, and design instruments for extreme conditions, are paving the way for future missions. Imagine spacecraft exploring other Kuiper Belt objects, or even the Oort cloud, a hypothetical sphere of comets enveloping our solar system. Pluto is a stepping stone, a proof that we can reach the outer edges of our cosmic neighborhood. Now let's address the elephant in the room: the idea of a catastrophic event involving Pluto. While the notion of a Pluto-Neptune collision is scientifically unfounded, it's worth exploring why such ideas capture our imagination. A collision in the outer solar system would be a spectacular event, releasing energy equivalent to billions of nuclear explosions. Pluto, being much smaller, would likely shatter, sending icy debris scattering across the Kuiper Belt. Neptune's thick atmosphere might absorb some of the impact, but its orbit could shift slightly, rippling through the solar system's gravitational web. For Earth, the direct effects would be minimal. After all, we're billions of kilometers away. But the scientific payoff would be immense, offering a rare chance to study high-energy events and their aftermath. Yet, this scenario remains purely hypothetical. The real drama lies in what Pluto's orbit tells us about the universe's fundamental laws. Gravity, the force that binds planets, stars, and galaxies, is at the heart of Pluto's story. Its orbit is a living example of celestial mechanics, where every movement is governed by precise mathematical relationships. For scientists, this is thrilling enough without inventing doomsday scenarios. And for the rest of us, it's a chance to marvel at the complexity of our solar system, where even a small, icy world like Pluto can teach us profound lessons. Pluto's journey also connects to broader questions in physics. The gravitational dance between Pluto and Neptune is a small-scale version of the interactions that govern galaxies and black holes. Some physicists, like Michio Kaku, explore how these forces tie into theories like string theory, which seeks to unify gravity with the quantum world. While a Pluto-Neptune collision wouldn't directly test string theory, studying extreme gravitational environments, like those near black holes, could. Pluto's orbit, stable yet eccentric, reminds us that the universe operates on principles we're still working to fully understand. As we look to the future, Pluto's story is far from over. Astronomers continue to analyze New Horizons data, uncovering new details about its atmosphere, moons, and surface. Future missions to the Kuiper Belt could reveal more about this distant region, perhaps discovering new dwarf planets or clues to the solar system's origins. Pluto's orbit, with its intricate resonance and gravitational ties to Neptune, will remain a focal point for studying celestial dynamics. It's a reminder that even the smallest players in our solar system have a role in the grand cosmic play. So, why does Pluto keep us captivated? It's more than just a distant dot in the sky. It's a symbol of exploration, a challenge to our definitions, and a testament to the beauty of the unknown. Its orbit, weaving through the Kuiper Belt, tells a story of stability amidst chaos, of tiny worlds holding their own against the giants. As we peer deeper into the cosmos, Pluto stands as a beacon, urging us to ask questions, seek answers, and dream of what lies beyond. Whether it's through a telescope, a spacecraft, or the equations of celestial mechanics, Pluto invites us to keep exploring, to keep wondering, and to keep chasing the mysteries of our universe.